At this point in physics, there are 5 forces that we generally are thinking of, and those are gravity, the normal force, the frictional force, tension, and an applied force. And we use these forces to think through any sort of situation, labeling them often within a free body diagram or an FBD. Let's talk first about free body diagrams. So when you draw a free body diagram, there's a few rules that you're expected to follow. For one, whether a force is a push or a pull on an object, you always draw the arrows coming from a dot that represents the object, not pointing toward the object. So this diagram on the left is the way you are expected to draw those diagrams, so please get used to doing that. If we have an object that is extended, like this blue rod here, then the forces no longer come just from a dot, they come somewhere along that extended object. But notice that the arrows still point away from the object. They just have a particular location along the object's length. Recall too from our earlier discussions that if an object's weight is to be considered, like say this one here, this orange arrow would represent the object's weight, that we consider that weight to act at the center of mass of the object, which is usually just the very center of the object itself. All right, well, let's take a look at some of the specific types of forces and recall how to determine them. So gravity, or the gravitational force, is something we've talked a little bit about so far. So it depends on the object's mass and the value of little g. So you can go ahead and use 10 newtons per kilogram if you'd like. You can also be more official and use 9.81 or 9.8. Again, that is a choice. It's fine either way. It's really important here, though, to think about that g not as an acceleration, but rather a ratio between mass and weight. So we're not saying that the object actually moves or even accelerates at 10 meters per second squared. What we're saying is that for every 1 kilogram of mass, there is a force of about 10 newtons pulling it towards the Earth. Some things to keep in mind with gravity is that it should always point directly downward in your diagrams, regardless of what's happening to the object. It will be a part of just about every single problem that we do, unless the problem mentions that the object's mass is negligible or it can be ignored. Watch out for thinking that the gravitational force is equal to 9.8. That is not at all what I'm saying here. The ratio between mass and weight is 9.8. So it depends on how many kilograms we're working with. And g itself is never a negative number. When an object is only under the influence of gravity, then its acceleration is g, and we often consider down to be the negative direction. So all of those things come into play when we plug negative 9.8 into a formula. But g itself, little g, is a positive value of 9.8. All right, another pair of forces that come up in many situations are the normal force and the frictional force. These both occur only when an object is in contact with some sort of surface or with another object. So if there is any sort of contact, then there's going to be a normal force, and you can use either F sub n, or some resources may use just a capital N to represent the normal force. The normal force is always perpendicular to the surface. So when an object is on a flat table, that's usually how we're thinking about a situation, then our normal force does point straight up. But if that table is at an incline, then the normal force points at an angle. And if the object is being pushed against a wall, then the normal force will be horizontal. Okay, so it's the rule is that it's perpendicular to the surface, not that it points in a particular direction. Particularly coming out of our first year physics course, where we were looking at very select situations, it's very common for students to think that the normal force is just equal always to the weight force or the gravitational force. And that is not the case. So watch out for situations where that will not be the situation. Again, we will cover that in a lot of detail in our class. The other type of force that comes from contact with a surface is, of course, friction. And so if a problem mentions friction or mentions that the surface is rough, then we will have that frictional force. And you can use F sub F, or sometimes just a lowercase f is used for friction. Now, this force is always parallel to the contact surface. So you can see that between normal force and frictional force, we are covering like the entire direction compared to a surface. It generally points opposite to the direction of motion, although there are some exceptions to that that we will discuss. And later in our course, we will spend more time talking about static friction. Static friction is when an object is not actually sliding, but there is an intended motion, direction of motion that we will look at. The formula for frictional force, and there is finally a formula for this one, has to do with mu, which is the coefficient of friction, and the normal force. So these two surface forces are related to each other. And mu is a number generally between 0 and 1, always positive, and it represents how sort of sticky the two surfaces are compared to each other, like a block versus the table that it's sliding across. Mu is not a number that you memorize. It's different for every situation. But again, you should know that it's between 0 and 1 in almost all situations. This formula has an inequality in it, and that has more to do with the static friction ideas that we will discuss later. For right now, we will be thinking of it as an equality. All right. The fourth type of force that we will encounter is tension, which has to do with ropes, chains, maybe even someone's arm pulling on something. You can use a capital T or F sub T to represent that tension force. The key things to know about tension forces is that they always are directed away from the object and right along with the rope, right parallel to the rope. So you end up drawing them right on top of a string or a chain or whatever it happens to be. And that the tension force actually pulls in two directions at the same time. And so we'll have to kind of see how that looks. We'll look at an example here in a minute. The rope, or if a rope or a number of ropes are tied together at a knot, we should also recognize that there's no reason that the different ropes pull with the same amount of tension. So we should assume that they are all different. Let's take a look at an example where we see tension forces in action. So here we have a setup where some ropes are being used to suspend a mass down here, and also to keep this situation along with friction in place. So let's take a look at some of the forces that are acting. Let's first look at this knot. So when you have this place where three forces are coming together, each force needs to be considered a different value. So I've labeled these FT1, FT2, and FT3. And we would use some trigonometry and so forth to relate these to each other. So the other thing then to understand about tension forces is they do pull on either side of the rope. Right now, this force body diagram, or free body diagram, this is talking all about the pulls on that knot, on that little spot there. If I'm interested in what happens to this block over here, then I would instead be thinking about the tension force pulling to the right instead of pulling to the left. But notice that these two forces marked yellow, they would have the same magnitude, they are just in opposite directions. And so that's something useful to be aware of. Just kind of finishing off this block over here. The reason it's not moving is because the frictional force points to the left, and that exactly equals the tension force, causing this object to be in equilibrium. There would also be a normal force up, perpendicular again to that surface, and a gravitational force down. Again, gravity always points down in our pictures. All right, last type of force kind of covers everything else. So if there's something from outside the system exerting an influence, we would have an applied force, and I would often use F sub P for that, but there's really a lot of different ways of labeling that. And again, this is just something from the outside that does not fit into one of these other categories that we would call an applied force. If you'd like to see more examples of free body diagrams, there is another video available that you can check out.